Hello everyone. First of all, I would like to thank you for attending this presentation. We will be presenting for the next 20 minutes the paper entitled Pixel-Off Data-Augmentation Complementary Solution for Deep Learning Steganalysis. This paper has been accepted in the 2020 version of the HMMSec, authored by me, Marc Chaumont, Frédéric Combé, Amadou Damara, and Patrick Ba. This presentation will begin with an introduction and a context in which we will talk about what is steganography and Steganalysis, as well as the motivation that inspired this study. Then we'll present the proposed method, and we finish with a conclusion. So, what is steganography? Assuming that we have two entities, Alice and Bob, Alice wants to send a secret information to Bob through a public channel. However, this channel is monitored by a third entity called Eve. Steganography is therefore the art of hiding this secret information within an innocent digital medium called cover. That may be image, sound, text, videos, etc. On the other hand, Steganalysis is the technique used to detect the presence of hidden information within a cover. In recent years, Steganalysis has been a hot topic. With the emergence of deep learning and the success that has been achieved in the field of computer vision, Steganalysis research turned their attention to its adoption and application for Steganalysis purposes. Since 2015, many articles proposing Steganalysis models based on deep learning have been published. However, the most important one and those that have made a breakthrough in the field of Steganalysis are highlighted in this figure. What is important to note is the evolution of the depth of this model. So, since 2015, the depth of this model has gradually increased from 5 convolution layers to reach 10 to 14 convolution layers by the end of 2019. Now let's go back to the computer vision. Studies have shown that the performance of a neural network model is directly proportional to its depth. However, this conclusion depends directly on the amount of data. The graph shows that the deeper the neural network is, the better the performance. However, if the amount of data is not large enough, like in this zone or in this area, a shallow network may even outperform a deeper one. Now the question is whether this conclusion also applies to Steganalysis. To answer this question, a test over 4 Steganalysis neural network models were conducted. We use for that 2 shallow network and 2 deep network. This network were tested against an embedding algorithm named WOW with a payload of 0.2 bit per pixel while using different training sets. Small one, medium one, and a relatively large large one, which are noted both plus virtual augmentation. Taking the XUNet and SRNet examples, we can see that both networks achieve the same performance when they are used on a small train set, such as both. However, when the size of the train set increase, the probability of error is significantly reduced for SRNet compared to XUNet, which is a deeper neural network. So we can say that the same conclusion is held for Steganalysis. Now the question is, if we want to Steganalyze a small database, what are the options that we have to train or to be able of training a deep neural network? According to this paper, we have actually 4 possible solutions. The first one is to apply virtual data augmentation. This consists of applying flip, rotate, and rotate operation. The second one, or the second solution, is to use a database similar to the original database. The third solution is to capture new images using the same camera that were used to capture the image on the original database. And the last solution is to apply similar development to the raw images of the original database. By the development, we mean the numerical process that transforms raw images into its final format. So this solution have been proposed actually for a controlled environment such as a laboratory, but they are difficult, if not impossible, to use in a real life case scenario. For example, the first solution, the solution where we use a similar development, may be hard to apply. So even if we assume that we know somehow the use development, which is not always the case, raw images are usually not available due to the storage limitation. The second options, or the second solution, were the use of similar database. This solution is not easy to implement also because we don't have an objective measure to measure the similarity of two databases. So the only possible way to know that is to test them, which is time consuming. As for the use of similar camera, this solution is not practical, as it can be very expensive to deploy, not to mention the fact that it's not easy to define the camera used to capture images from original database, especially with the huge variety of cameras models that exist nowadays. As for the last solution, let's assume that we have a very small memory there, let's say 10, 100, that we want to Steganalyze. The variable data augmentation will increase the size of the database by a factor of 8, which is great. But the size will remain very small to train a neural network. So this solution is not enough. So this will leave us with no possible solution for live case scenario. To this end, we have conducted our study that has led to the proposal of the pixel-off technique. So what is the pixel-off technique? It is a new way to enrich a database in order to improve the CNN-based Steganalysis performance. This technique is efficient, generic approach, which can be used alongside with other data enrichment approaches such as virtual augmentation. This technique may be also used to build what we call sidechain aware database that we will talk about later. So in the following diagram, we present the overall flowchart of the pixel-off technique. The first phase is the cover preparation. The second one is the SCA generation. Once we have covers and SCAs, we start the training with the data augmentation, which is the pixel-off technique. So now we are going to talk a little bit more about the first phase. So this phase consists in generating the pixel-off version of the original database. For that, we first define a number, the number of pixels to be set to 0, which we call, or which referred as P, and then the pixel-off version of this cover are generated. So taking this example, we have these images. We are going to set P equal to 100, so we are going to turn off 100 pixels. Then the corresponding pixel-off version of this cover is generated. The dark pixel in this image represent the pixels that have been turned off. The second phase consists in SCA generation. For that, an embedding algorithm and a defined payload are used. Now, to demonstrate the impact of the pixel-off on the SCAs, we visualize the embedding modification probability obtained using SNU-word with a payload of 0.4 for each pixel of the cover images, and also in on its corresponding pixel-off version, which are the two pixels that we have seen before actually. So we have to know that the red pixels stand for the high probability and the blue ones for the low probability. So we can see that these two probability maps are not the same. But to better illustrate the difference between these two images, we adopt the visualization by elevation. So the pix stands for the pixels area where there is a difference between the embedding modification probability. One can observe that the probability between the two images are similar, except in areas close to pixel off. This occurs because a pixel of area is producing a sign in the image that is captured by the filter computing the cos map, such as those of SCA or WoW, and is identified as an area where the embedding is favorable, which means whose cost value is small, thus the modification probability is high. Thus, a STEGO image and its pixel off noisy version will not be the exact same modified pixel when the same message is embedded. This probability also interesting because it produces noisy STEGOs that are different from the initial STEGOs, but still statistically close. Once the cover and their STEGO are ready, we pass to the phase 3. So the two sets of covers, cover and cover V1, are grouped together in one set. Same for the two sets of STEGOs. Then we choose whether or not to apply their augmentation techniques. Once everything is ready, we initiate the model training. So now we are going to present and discuss the result of the conducted experiment. The first test is about evaluating the efficiency of our proposed method. In the following table, we keep the Steganalysis error probability of heterogeneity against two embedding algorithms, WoW and SCA at two different payloads, 0.2 and 0.4 bit per pixel. For that, we use base as the original bit database. So we will launch test with and without pixel off to train our model. We can see that by using the B1 learning set, which is which regroup the initiate learning set plus the 100 of version obtained using the pixel off technique, the heterogeneity error probability is decreased on average by 2%. The performance is even and further improved when we increase the initial training set twice. For that, we use both the 100 of version and the 256 version, which we'll note P2. Even better results are obtained when we accumulate 3 versions of the pixel off, 100 of and the 256 plus the 400 of. We obtain an improvement of 2 to 4% for WoW and 5 to 6% for SCA. For the second setup, we use the same database, the same enrichment method, but we use another Steganalysis, which is CovPoolNet. We can notice that the pixel off technique worked also for CovPoolNet, as the error probability decreased progressively each time we increase the initial training. The error probability is decreased by 2 to 3% for WoW and 3 to 5% for SCA. Also, we note that even better results are obtained when we accumulate pixel off technique with the virtual augmentation technique. Now, in an attempt to understand the underlying properties resulting from the use of the pixel off technique, we evaluate two other noise and compare their performance to the pixel off enrichment. The first noise is the salt and pepper, which we use on two different density, D equals 0.05 and 0.0016. The second noise is the Gaussian one. So we can notice a drop in performance, which is equal to 1 to 2% when we use Gaussian and salt and pepper with a density of 0.05 compared to the classical scenario. This suggests that the addition of high power noise can lead to an important modification of the initial statistical model of both cover and Stegall continent. Thus, it provokes a mismatch between the training and the test set. On the other hand, using weak noise signals such as the pixel off or salt pepper with d equal 0.0016 can improve the detection accuracy by almost 2%. We can then conduct that only low power noise efficiency noise affecting very small percentage of pixels can be useful for data enrichment. One should conclude by now that the pixel of enrichment inside the learning to be more sensitive to areas around switched off pixels, since these areas are now associated with strong embedding probabilities. This may encourage the convolutional kernel to learn local weight more sensitive to modified areas. To investigate this hypothesis, we conduct a test where we modify the pixel off technique so that pixels switches off are chosen by taking into account the side channel information. So more precisely, instead of randomly switching off 100 pixels of the whole image, we switch off the same number of pixels while considering only the 10% pixels with the highest embedding probabilities, which we'll note here, both plus high p. Then we test while considering only the 10% pixels with lowest embedding probabilities, noted both plus low p. We can observe that the detection accuracy is reduced by 1% when the modified pixels are concentrated on pixels with low modification probability. On the other hand, the results are improved for the scenario where we consider only the 10% pixels with the highest embedding probability. These results show that the pixel off technique may be a possible way of doing side channel aware Steganalysis by generating side channel aware training set. To conclude this presentation, we emphasize that the pixel off technique is a novel technique for data-based enrichment for Steganalysis Steganalysis, which is close in principle to noise addition, but made so that the pixels distribution of the resultant image remained as close as possible to the original images. This technique is efficient, simple, and easy to implement, come with low complexity. Besides, it may be used alongside with other data augmentation such as virtual augmentation. This technique may be used for building information database. However, more studies need to be done. So this will be all for me. So thank you so much for your attention, and I am open for questions. Thank you so much.